Okay, so like I said, I accidentally posted an online homework assignment on Canvas. That was for a different class, so please ignore that. Okay. Today I'm going to just cover what's called implicit differentiation. So before I do that, I want to at least tell everybody what an implicitly defined function is, or an implicit curve, and the difference between what we've been working with, which are called explicit functions. Okay, so 3.5, implicit differentiation. Okay, and it starts by, let's look at the difference between explicitly defined functions and implicitly defined functions. Okay, which actually aren't even necessarily functions. Okay, so first of all, that's kind of one thing that's a little strange. Okay, so I'm going to make a list over here. Explicit functions. And then over here, I'll write down what an implicit function looks like. Okay. So explicit functions, these are things that we've been studying the whole time, where the dependent variable can exclusively be written as a function or equation of the independent variable. So, we've been working with things like x squared over 1 plus x squared, or, another example would be y equals the square root of x plus 2, or I could do y equals the square root of 25 minus x squared, or y equals negative square root 25 minus x squared. And there's a whole bunch of other ones I could write too, like y equals 2e to the 2x. Okay. So anytime you already have the dependent variable solved for and it's written as an expression of just the independent variable, that's what an explicit function is. That's what we've been taking derivatives of the whole time. Okay. Now, implicit functions. Okay, this time I might have something like x squared plus y squared equals 25. Okay. So basically all an implicit function is one in which the dependent variable is not solved for. Okay. Another example would be like 2x squared plus 3y cubed plus 2y equals 4.
So would you solve for one variable?
If possible. So what I would maybe want you to notice, and I'll just use these two, this one you could solve for y, but you actually have two choices because y would be plus square root of 25 minus x squared or the negative. Okay. This one though, you wouldn't be able to solve for y because of the mixture of powers, right? You've got a y cubed and a y term. Okay, so in general, an implicit function cannot be solved for the dependent variable. Okay, and actually the difference here, these are both going to give you graphs. Right? An explicit function will give you some curve that passes the vertical line test. Most of the time, implicit functions, right? Like basically the graph of this would be all the pairs of points x, y that you could plug into this equation and get 25. Okay. Does anyone recognize what this equation would give you? Anybody seen that before? X squared plus y squared equals 25. The second one isn't really very recognizable. But I'll say this, x squared plus y squared equals 25 is the equation of a circle centered at the origin of radius r equals the square root of what's on the right. So that's actually just the equation of a circle centered at the origin. So I could draw the graph. since the radius is 5, you could go 5 units up, 5 units down, 5 units right, 5 units left. Okay, and that would just be the curve associated with x squared plus y squared equals 25. Okay, now just looking at this, right, again, all the pairs of points x and y that satisfy the equation land on this circle. For instance, up here, this is the point 0, 5. If you plug in 0 for x and 5 for y, you will get 25. So that would be a point on the circle. And to be honest, I have no idea what this looks like. Okay. Now, you could solve for y in this. So if you started to solve for y, what you're going to get is plus or minus the square root of 25 minus x squared. So you'd subtract the x squared on the right and take a square root, and you end up getting a plus or minus. Okay, so that's why I purposefully did this. If you try and solve the first equation for y, you actually get two separate functions, the positive square root and the negative square root. Okay, y equals the square root of 25 minus x squared is the top half of the circle. Y equals negative 25 minus x squared is the bottom half. Okay. So basically the only hope of getting an explicit function out of an implicit one is if you can solve for y. Okay. But that isn't necessarily always the case. In general, an implicitly defined function or implicitly defined curve cannot be solved for the dependent variable. But we could still find rates of change and still find slopes of tangent lines without actually having to try and solve for y. So that's the whole point of this section. Can we still find rates of change without solving for the dependent variable? Okay. In some cases you can solve for the dependent variable, like most circles you can solve for y, but that'll always give you a top half and a bottom half. Okay. So in this case, this implicit function can be separated into two explicit ones, one giving you the top half of the circle, one giving you the bottom. Okay, but this equation over here, or this implicitly defined curve, there's no way to solve for y. You could try all day and it won't work. Okay, so you can't solve for y just as a function of x. Okay, so this is the whole idea of implicit differentiation, is if I can't solve for the dependent variable, how do I find the rate of change? Or the slope of any tangent line on the curve. Okay. So, let me now kind of describe the method. So put explicit functions behind you for a section. Right? We know how to take all the derivatives of these, either using quotient rule here. This is the general power rule. Same thing here. Either one of these would be general power rule. This one you'd have to use the chain rule on. Okay. But what do we do on the right-hand side? What if I want to find y prime if I can't solve for y first? Okay, that's the goal. So given an implicitly defined function, or I'll just put defined curve. Okay, all the graphs of these things are going to give you some curves. Some of them might be circles, some of them might be ellipses, other ones might just have crazy weird shapes. Okay, who knows what they're going to look like. So given an implicitly defined curve, how do we find the rate of change of the dependent variable? Okay, so that's the question. So first of all, you're going to have two variables. You have to make a decision. Which one are you going to treat as the dependent variable? Okay. I think what I'm going to do is just do this through example. Okay, so example 1. So this time I gave you, if you think about the graph of x squared plus y squared minus 16 equals 0. Okay, so consider the graph of that. We're going to find y prime, which is the same as dy dx. So if I write y prime, I'm treating y as the dependent variable and x as the independent variable. And then what else did I say? Find, and the slope of the graph at x equals 2. Okay. And maybe some more background to this. You might have a price-demand function in which you can't isolate the price or the demand. Okay, so I could still find the rate of change of demand with respect to price, even without even solving for one of the variables. Now, the graph of this, you could move the 16 to the right. So if I draw the graph of this thing, the graph of x squared plus y squared minus 16, and don't worry, you're not going to have to graph these on the test. The idea is just you're supposed to understand that these implicitly defined functions or curves, they give you exactly that, some curve. Okay? And you're not always going to know what it looks like. It's just with circles you have the benefit of knowing what the curve looks like. So I can draw the curve. Here's the x-axis, or here's the y-axis and x-axis. And the radius is going to be positive 4. Okay. And then if I'm trying to find slopes of the tangent line, or if I want to find the slope of the graph at 2, you're actually going to have two places. You'll have a point down here when x equals 2. We're going to find the slope of that tangent line. You're also going to have a point up here where x is 2, and we're going to find the slope of that tangent line without even solving for y. Okay? So here's the idea. What you do is you treat y as a function of x. Okay? Meaning if I have something like y squared, that's really a function squared, so you'd have to use the chain rule when you take the derivative. Okay? Now, maybe I should just... Now, is y really a function of x looking at the curve itself? Because it fails the vertical line test. So y is really not a function of x. So this is kind of misleading. We're going to pretend it is, even though it isn't. Okay, and that's why I was saying, look in the textbook. This is a little bit weird. You treat y as a function of x, even though looking at the graph, it is totally not a function of x. Okay. Now, if I have to write this in, and we'll do it, i.e., we're just going to pretend y is some f of x. Okay, and then what we're going to do is we're going to take the derivative of both sides with respect to x. And is it okay if I write WRT for with respect to? Okay. Okay. So I'll do that on the left. I'll write d over dx of this x squared plus y squared minus 16. And I'll also take the derivative with respect to x of the right-hand side. Right? If you have an equation, if both sides are equal to each other, then the derivative of both sides should be equal to each other. Okay? Now you can still take the derivative term by term on the left-hand side, but I'm going to come off to the side and do this. Or let me do this first. Okay, so the derivative with respect to x of x squared, that's just going to be 2x like before. I'm going to write d over dx of y squared. We'll worry about how to do that in just a second. And then what's the derivative of a constant negative 16? That's 0. So we're just taking the derivative with respect to x of all those terms. And what's the derivative of 0 on the right? Still 0. Okay. All right. So how am I going to take care of this? So what I might have to do to help everybody is pretending that y is equal to f of x. Okay. Let me come off to the side. So d over dx of y squared is just like doing d over dx of f of x squared. Okay, so we're really using the chain rule. We're treating y as a function. Okay, so the derivative isn't just going to be 2y. Okay, that's what you have to be careful of. Now, what does the chain rule say? If you have a function to a power, you take the derivative of the outside first, right? So the 2 comes down. What happens to the inside?
Stays the same.
Stays the same, so you still have f of x in here. You raise it to the next lowest power, which is 1, and then what do you want to make sure you don't forget on the end?
Multiply by the derivative.
Multiply by the derivative of the inside, which is f prime of x. And now what I'm going to do, I'm going to rewrite this in terms of y. Right? I'm pretending y is this function of x. So now this would become 2 f of x is y times, and f prime of x, another notation for that is just y prime. Okay. So whatever the dependent variable is, you have to use the chain rule, because you're treating the dependent variable as a function. Okay, it's not just a variable anymore. Okay. So when I come back over here, it's really 2x plus 2y, y prime, and then I have an equals 0 on the right. So again, whatever you're treating as a dependent variable, you're treating it as a function of x. So that variable to any power, you have to take the derivative using chain rule, or modified power rule, or whatever you want to call it. Okay. So again, since we're taking derivative with respect to x, the derivative of x squared is what we typically would do, 2x. But since y is being treated as a function, the power comes down, the inside stays the same, and you have to multiply by the derivative on the outside. Okay. And then now we can solve for y prime. So 2y, y prime is going to equal, we'll subtract 2x to the right. And then y prime, if you divide both sides by 2y, the 2's will cancel. You'll just get minus x over y. Okay. And this is what's really weird. Your derivative is actually going to be in terms of x, the dependent variable and the independent variable. So that's kind of cool. The slope on this circle, the slope of the tangent line is just minus the x coordinate over the y coordinate. And that would give you the slope of the tangent line on this circle. Okay, yeah?
How do you know to solve for like y prime, not just y?
I think the question says find y prime.
Okay, yeah.
So in that case, I'd have to solve for it. And like I said, when you do implicit differentiation, that's all implicit differentiation means. It means take the derivative without solving for the dependent variable. You just take derivatives of both sides, and you treat the dependent variable as a function of x. Okay. Right? So anything with x's, you take the normal derivative, but since we're treating y as the dependent variable, we have to use chain rule. So the 2 comes out front, the next lowest power is 1, and then you multiply by the derivative of the inside, which is y prime. Okay. And again, I know it's really strange. You're pretending y is a function of x, but it's not at all, right? Because the curve fails the vertical line test. Okay. And like I said, this is the reason, right? If you treat y as a function of x and then take the derivative, you do the power rule on the outside, the inside stays the same, and you multiply by the derivative, and then converting everything back to y is f of x is y, f prime of x is y prime. Now, you don't need to do that, but if it helps you remember, okay, always write your dependent variable as an f of x or f of t. Okay. All right, and then we need to find the slope of the tangent lines, or the slope of the graph at x equals 2. Notice, though, on the circle, there's actually 2 places where x is equal to 2, and there's a way of seeing that, right? Because you're not going to know what the graphs of these look like. So how did I know there was 2 places? So what I can do is, you'll take the original curve, or equation for the curve, I can plug in x equals 2, and then solving for y is going to give me 2 values. Okay, so when x equals 2, that implies you have 2 squared plus y squared, I guess now equals 16. I'll move the 16 to the right. 2 squared is 4. You can subtract 4 to get y squared equals 12. So y is going to equal plus or minus the square root of 12, which is plus or minus 2 root 3. 12 is 4 times 3, and the square root of 4 is 2, and the 3 stays under the radical. So those would be the two y coordinates of these points. That would be 2 root 3, and that'd be minus 2 root 3. Okay. And then now to find the slope of the tangent line part. Okay. So you're going to have to do two of them. So here's the notation you can use. You can do y prime. Does anyone remember me doing the bar notation for evaluating a derivative? And you're going to do this at the point 2 comma 2 root 3. And then we're going to find y prime at the point 2 comma minus 2 root 3. And those will be our two slopes of the tangent line. Now, just looking at the picture, what's the sign going to be on the first one? So if I'm looking at the slope of the tangent line here, we should get a negative, right? Because it's a decreasing. And then for the other point, you should get your y prime should end up being positive. So, and then now coming back over here, y prime was just minus the x coordinate over the y coordinate. So this will just be minus 2 over 2 root 3. And you get minus 1 over root 3. Again, that agrees with what we see in the picture. The slope should be negative because the tangent line is decreasing. Okay. And then this one's going to be minus 2 over negative 2 root 3. And that just gives us positive 1 over root 3. And that would be the final answer. We found y prime, and we found the slopes of the tangent line when the x coordinate was 2. Otherwise, the only other way I could solve this problem is if I solved for y, that gave me the top half. Right? And then I'd have to find I could solve for y and get the equation of the bottom half, and then I'd have to take two derivatives, and I'd have to plug 2 into each of them to get those slopes. That way would also work. Okay, but the problem is you're not always going to be able to solve for the dependent variable. So that's going to be the case in example 3. Both example 1 and example 2 could have been done with the old form of differentiation, but you'd have to do all that algebra first. Okay. All right. So again, what you do is, if they're telling you to find y prime, you're treating y as the dependent variable, and then you have to take the derivative with respect to x on both sides. Anything with x's, you just take the derivative as you normally would, but since you're treating y as a function, y squared has to be differentiated using the chain rule to get to y prime. Then you solve for y prime. And then what we had to do was, if we want the slope on the curve, or on the slope of the graph when x is equal to 2, I had to find the y coordinates of those points using the original equation. And then you just plug those coordinates into y prime to get the slope of the tangent line. Okay. If we wanted to, we could find the equation of the tangent line too, but we won't do that here. Okay, so example 2. Anybody have any questions first? Maybe just more examples? Anybody still need this part? Okay. Now, this is another one that technically could be solved for one of the variables, but we're going to do this implicit differentiation method. So this time we're going to use implicit differentiation. We're going to find ds dt if the curve or the function is given implicitly by this equation. So 2st plus s plus 2 equals 0. Okay. Now again, I could factor an s out of the first two terms. I could move stuff around. I could solve for s here and find the derivative of that function with respect to t. Okay, but I'm not going to do that. We're just going to leave it as is, and we're going to take the derivative of both sides with respect to t, because the dt is in the denominator. So this means we're treating s as the dependent variable, and we're treating t as the independent variable. Okay, now, if I take the derivative with respect to t on both sides, the s prime or the ds dt will show up somewhere, and then we'll have to solve for it. Okay. I'm also going to use the ds dt notation instead of the s prime. But they're the same thing. S prime and ds dt are the same. Okay, so any ideas? T is the dependent or the independent variable. So this time we're treating s as a function. So if I rewrite this a little bit, that's really 2s times t. So you have a first function 2s times a second function t. Okay, so the derivative of the first term, I'm going to write it down this way. It's the first function 2s times the derivative with respect to t of the second function. So I'm doing first times derivative of the second, plus the second function, which is t, times the derivative with respect to t of 2s. So now I'm just taking the derivative term by term. And I use product rule on the 2s times t, plus, and then it's the derivative with respect to t of the term in the middle, s. But here's one we should know. The derivative of a constant is always 0. Okay? So that's the left-hand side, and then the derivative of 0 on the right is also 0. Again, I'm writing more than you would need to on your homework. Okay? I'm writing in all these differential operators to tell you where I'm taking derivatives. Okay. So it's 2s times. Now, what's the derivative with respect to t of t?
1.
Just like the derivative with respect to x of x is 1. So that's 2s times 1 plus t times, okay, the derivative with respect to t of 2s. Remember, s is not the independent variable, it's the function. So what does the constant multiple rule say? The derivative of a constant times a function is going to be the constant 2 times the derivative of s with respect to t. That's ds dt. So really all I did was pulled the 2 out front, and then the derivative of s with respect to t is ds dt. You could have also written s prime if you liked. I really don't like using this notation for implicit differentiation. I like using the prime notation better. And then plus, what's this one? What's the derivative of s going to be?
1.
So careful, it's not going to be 1 again. You either write s prime, or in the notation we're using, the derivative of s with respect to t is just ds dt. And then you have a 0 on the right. And like I said, anywhere I wrote ds dt, you could have written s prime. Okay. And then now we have to solve for ds dt. So this is where I was saying, I think maybe this section's not super hard, it just takes a while to get used to it. Okay, treating a variable as a function is maybe what throws people off sometimes. Okay, so we'll just have to make sure we get some practice. Now I'm going to simplify a little bit because this becomes just 2s times 1 is s plus, and then you have 2t ds dt, and then plus a ds dt. And then you have equals 0. Okay, now if you look at the second two terms, they both have a factor of ds dt in common. So this would be, is it okay if I subtract the 2s to the right-hand side? So on the left, if I factor the ds dt out, you have 2t plus 1 ds dt. And on the right, I'll get a minus 2s. All right, if I distribute the ds dt back through, I'd get what I started with. Okay. And then finally, if you divide by the 2t plus 1, ds dt is minus 2s over 2t plus 1. That's an S2, not a 5. I don't know if you guys have realized that my S's are curly and my 5s have the... So hopefully I make it clear enough. All right, let me just look through this one more time, make sure I didn't screw anything up. Okay. That would be it. That'd be ds dt. And then if I wanted the rate of change of s with respect to t, I'd have to give you an s value and a t value. Actually, technically, I would just have to give you 1. Because if you knew the value of t, then you could solve for s. Okay. And then that would allow me to find the rate of change. And again, what you ought to be thinking, this original equation gives you some curve. And to find the slope of the tangent line at any point, I would just take the coordinates of that point and plug it in here. Okay. So yeah, it's a little weird. It's a matter of getting used to the fact that you're treating s as some function. Okay, so 2st is really the function 2s times t. So again, I had to use product rule there. Any questions or anything else? Yeah.
So how did you pull a 2t plus 1 out of that?
Okay, so you're okay with how I subtracted the 2s over.
Right.
And then the 2t ds dt, that's one term.
Yeah.
And then plus ds dt. Just treat that like a variable x. I just factored the x out. And then what's left over is 2t plus 1. Distribute this back through.
Oh, okay. Okay.
And if I distribute this back through, I get 2t ds dt, that's this term. And then ds dt times 1 is just ds dt.
So you really factored the ds dt out of? And
Yes, out of these two
one is
terms.
what's left over. Okay.
Yep, yeah.
Okay, I just want to make sure I'm understanding this, because the problem we just did before, we had to go to the side to find y prime, but this one, we didn't have to, like, go to the side.
Well, ds dt is s prime.
But on, like, the problem we just did, we had to, like, pause on finding it to, like...
Yeah, I went off to the side to show you the derivative of y squared is 2y y prime. Is that what you mean?
Mm-hmm. But we didn't have to do it for this one.
No, I didn't do it on this one because I didn't have s to any powers.
Okay.
So like if this was an s squared, I would have had a 2s s prime show up. I think you'll see that when we look at the next example. Because in the next one, I also am taking a derivative with respect to x. Yeah, you'll see it you'll see it show up in the next example again. And then if we have time, I'll make up one more. Okay. So yeah, this time it was a little bit different because I didn't have my dependent variable to any powers.
Okay.
All right. So one thing I want to say is once you figure this out, you're gonna realize this is no different than derivatives in the first place. It just takes a while getting used to treating the dependent variable as a function. Okay. Okay. So let's do one more before I give everyone one to try. So the next one I think is a price-demand relationship. Okay, so the number of items X sold at a price of P dollars is given by this equation right here. Okay, so maybe some economists realized that the relationship between demand and price was given by an equation like this. Okay. Now, the only problem here is, what do we want to do? We want to find the derivative, the rate of change of P with respect to X. So find the rate of change of price with respect to demand. Okay. Well, let's write x. Okay, so really all that's saying is find dp dx, or if you like, p prime. Which I think this time I'll do the prime notation. Looks a lot better writing the prime notation than the Leibniz notation. Okay, now, why do I have to use different implicit differentiation this time? Since that's a quadratic in p, there's really no way to solve for p. Okay. There's no way to isolate p as a single function of x. Okay. As a matter of fact, if you were treating, let's see, if you're treating p as the dependent variable, this would actually, the graph would be a sideways parabola. Again, it would fail the vertical line test. But like I said, there's really no way to isolate p this time. Okay. So I have to take the derivative implicitly. So everybody, hopefully everyone realizes this now. If you're finding the rate of change of a variable with respect to another, okay, the rate of change of the variable, that's going to give you dp in the numerator. And then with respect to another variable, that's giving you the dx in the denominator. So you're treating p as the dependent variable and x as the independent variable. Okay, but we're going to just write it as p prime. So now, since we want dp dx and we're treating p as the dependent variable, we'll take derivative with respect to x on both sides. So you're going to do d over dx of the left side, just x. And on the right, you're going to do the derivative with respect to x of p squared minus 2p plus 100. Okay. Now, what's weird? You're taking the derivative with respect to x on the right. Anybody see any x's over here? Nope. Because we're going to treat p as a function of x. Okay. If you have to go onto the side and rewrite like p equals f of x and then take the derivative and then replace the f of x's with p's at the end, you can do that. Okay. And if anybody needs me to show them, I will. Now, the derivative with respect to x of x. Oh. So what's the derivative of the left-hand side? If x is the independent variable and I'm taking the derivative with respect to x, you should just get 1 on the left. Okay. Now, if you're taking the derivative with respect to x of the dependent variable, here's where you have to use the general power rule. Because really, p is a function. It's the inside function. And the square, the outer power, that's the outside function. So the derivative of p squared is going to be 2p to the first power. So that's the power rule on the outside. And then the inside function is p, so you have to multiply by the derivative p prime. Okay. And sorry, that's supposed to be a 1. That's the derivative of the first term. And then it's going to be minus 2 times the derivative of p with respect to x. So it's either dp dx, or if you like the prime notation, you can do minus 2p prime. And then the derivative of the constant 100 would be 0. Okay, so that's all you get for this one. The derivative with respect to x of x on the left is 1. And then that's not really a variable anymore. P is now a function of x. So we have to use the chain rule in the first term. Then it's minus 2 times the derivative of p, which is p prime. And the derivative of the constant is 0. Okay, and then is it too bad to solve for p prime now? I think both terms on the right have p prime. So 1 is equal to p prime times 2p minus what? 2. Okay. And then finally, p prime is 1 over 2p minus 2. Which is kind of interesting. The rate of change of price with respect to demand only depends on the price. Doesn't even depend on x at all, the number of units demanded. Yeah?
So when you're taking the derivative of minus 2p, since it was a dependent variable, that's why it's like 2 times the p prime.
Yep, we're using constant multiple rule because it's minus 2 times the function. So the derivative is minus 2 times the derivative of the function. And the derivative of a function p is p prime.
But if it was x, it would just be.
Yeah, if this was minus 2x, the derivative would just be minus 2.
Okay.
Yep.
And you don't use the chain rule in the second one because the exponent's 1?
Yep,
The first power?
because we just have to the first power. Right? It's just like if this was f of x, the derivative would just be f prime of x.
Okay.
But if it was f of x squared, you'd do the power rule on the outside, you'd keep the p the same, and then multiply by the derivative of the inside p prime.
Okay.
So it's just like you're doing the derivative of f of x squared. Right? So you're pretending p is a function of x. So the 2 comes out front, you reduce the power by 1, the inside will still be p, and then you would multiply by f prime of x, which in this case would be p prime. Okay? And then other things you could do here, and I'm sure I assigned a homework problem. I did assign homework for this section. You know, you could say, what's the rate of change in price when the price is $4? Then you just have to plug 4 into p prime. So like for instance, you know, what is the rate of change of the price with respect to demand x, sorry, let's write price p, with respect to x, when the price p is, say, $4. I don't even know what the good is. I don't even think I told you. I think we're just working with number of units, right? I didn't tell you whether it was jerseys or shirts or shoes or whatever. Okay, so if I wanted the rate of change of price with respect to the number of units demanded, just in case this shows up on the online homework, because I know there's a couple business and economics ones. So now I can do, what's p prime when the price is $4? And in that case, you would just do 1 over 2 times 4 minus 2, and I would get 8 minus 2, you'd get 1/6. And then, anybody know what that is? Is it like 0.16? Okay. Okay. So the rate of change in price when the price is $4 is 1/6. And then let's write down our units. This is why the dp dx notation is helpful, right? Because when you're writing down your derivative as a rate, the top is going to be change in dollars, and the bottom is going to be change in units. Okay, so this would just say dollars per unit. Okay, so when the price is $4, right, each additional unit that's demanded would lead to a 16-cent increase in the price. Right, so if somebody demands another unit, the price is going to increase by 16 cents. Okay. Which is kind of weird. Doesn't that go against how it usually works? If you increase the demand, usually the price would drop. But we all know there's certain goods for which that kind of violate that rule. Or again, the only one I can think of is like luxury cars. Okay. Or I guess, isn't it true for cars too? Like if you demand, like say an extra gallon of gas, isn't the price going to increase? Right? Like in the summertime, don't people demand more gas because people are traveling more, but they raise the price. Okay, so this would make sense in the gas scenario. Yeah.
Isn't that just because it's a limited?
Because it's what?
It's a limited quantity.
Yeah, that might be the case. And there, like I said, when it comes to economics, I would almost bet most of you know more about the terminology than I do. So, how about just one more real quick one for everyone to try? Okay. Okay, so let's call this example 4. Let's find y prime if So this time I kind of gave you one that was a little sneakier. Let me write a couple relevant formulas down for everybody. I don't think the derivative of this, this, or this is very hard, but that's going to be the hard part. So first of all, remember that d over dx of e to a function of x is the same thing times the derivative of the exponent. Okay, but since you're treating y as a function, the function and the exponent's a product, so you'll have to do a product rule to take the derivative of that. So see what you can come up with in a couple minutes, or at least think about it for a second, and then I'll show you how to finish that off. So take the derivative with respect to what variable?
Why?
Well, if you're finding y prime, you're treating y as the dependent variable.
Alright, so x.
So with respect to x. So you're doing d over dx on both sides. See in the meantime if anybody has any ideas. The derivative is what you use.
Do the x, y times y the function, x values.
Sure, but we've got to do the product rule. So first function times derivative of y plus y times the derivative of x.
Oh.
Because right, if you're treating y as a function of x, x times y would be the product of functions.
Plus
Can we come up with any guess?
I
times
don't know
x
exactly.
prime, which is just 1
Okay. It's okay if you're not sure what it is. You do it together. Let me see. You got squared. Now, this is chain rule 2. This comes out front. So you it's what you have times the y prime.
X, y times b. And you just put the x, y.
Ah, yes, yes. And then, since you're multiplying here, you need an extra set of parentheses. Here and there, yes. Okay, so let me help everybody with this one. Okay, so this one's kind of tricky. They can get messier, trust me. I don't think we're going to make them very difficult for the sake of what we're doing. Okay, so if I want to take the derivative of e to the xy, so up here in the exponent, that's some function of x, right? X is a function of x, and we're treating y as a function of x. So this is actually a product of functions. Now, e to a function of x is you're going to write the same function down times the derivative of the exponent. So I think at least you should know you have an e to the xy, the same thing, times, now, since the exponent is a product, x is a function of x and y is a function of x, you have to use the product rule. So it's going to be the first function is x times the derivative of y, which is what we're trying to solve for, y prime. So that's first function times derivative of the second, plus the second function y times what's the derivative of x going to be? 1. So what should this next term be? It should just be y times 1. Okay. So again, what you should be seeing here is x times f of x. Right? It's really y, but you should be thinking function of x. So it's the first function x times the derivative of the second, the derivative of y is y prime, plus the second function y times the derivative of x, which is 1. Okay, so that's what it would be. It would be the same thing, e to the xy, but x times y is really a product. You have to use product rule. So it's the first function x times the derivative of y, which is y prime, plus the second function y times the derivative of x, which is 1. Okay. And then what about the next term, minus 4y cubed? Again, y is a function of x. So you do the power rule on the outside. So what did we get for that one? Anyone want to share?
All y squared times y prime.
Okay, so you get the minus 12. The inside y stays the same. The power reduces to a 2. But we're treating y as a function of x. So we have to multiply by the derivative of the inside function, y prime. Okay, if you're trying to find y prime, y is the dependent variable. The inside stays the same. The power comes out front. Lower the power by 1 and multiply by the derivative of y, which is y prime. It's the same thing you're doing before. It's instead you need to make that connection. You don't see y as y. You see y as a function of x. Okay. And then how about the derivative of 2x? X is just the independent variable. So the derivative of 2x is just 2. And then the right-hand side would just become 0. Now we're run out of time. I actually stole like 2 or 3 minutes. But you'd have to multiply this stuff out here. You'd have to isolate the terms with y prime on one side, move the other stuff over. You'd have to do some factoring. Okay. So we can maybe finish that up tomorrow, but we're out of time. So now you'd have to solve that for y prime.
It's not too hard. That's the easy part, in my opinion.
Nothing in math is hard once you get it and you've done practice. But yeah, certainly, especially something new like this that's weird compared to everything we've been doing already, just make sure you're getting the extra practice.
Well, minus 2 over.
Now, you know